Yeah, sorry for the abrasive abstract. I have co-authors I can blame. Anyway, heat maps. Don't use them. That's the high order bit, as we say in computer science. If you're willing to learn some details, well, maybe use them a little bit sometimes, but remember, no matter how good you might be at heat maps yourself, you're going to be stuck with an audience that really is probably going to be prone to misconceptions. They're kind of like small-scale maps in that regard. The higher order bit is don't use them. I hope that's not news to you. Of course, I'm exaggerating, I think. Anyway, be careful. Let's get straight what we're talking about. This is a heat map. This is not a heat map. A choropleth map can approximate a heat map if you sort of blur your vision a little, but the way you make one is quite different from a heat map. This is sometimes called a heat map, but it's not what we're talking about either because it's a method of construction that and interpretation differ. This is also not a heat map of the kind that we care about here. Why is this not a heat map? It's because choropleth maps show they don't show you what I'm messing around with on my iPad here. That's what they show. So you take all your data samples within the boundary, you aggregate them, and you color the entire bin with one color to represent that aggregation. That's what we do for a choropleth map. So why is this not a binning method? It's because you are taking essentially, in concept anyway, you're taking a sample at every single pixel, a sample of your information, or you're an interpolation of it. You might say, okay, well, a pixel is a bin. And you might think you're clever by saying that. It's sort of true, but if you were to zoom in into the map and expand those pixels, they would disaggregate into new different pixels. And so they're not really bins. And the aggregation method, by the way, is also rather different. So how do we make heat maps, now that we're clear on what we're talking about? I'm going to say the word pixels a lot because they're a good proxy for just a tiny unit of visual space. And typically that's how we're dealing with them these days. Let's say you have some phenomenon and you have some measure of the phenomenon that relates to density or intensity or magnitude or count of the phenomenon, and this measure varies across the space. Maybe you're measuring rainfall for a year across billions of different locations. Maybe it's property crime incidents, maybe it's species count, maybe it's active hair follicles per square inch. That's a topic of interest on my head. If you already have a density measure for every location coinciding to a pixel, then making the heat map is quite easy. Relate the magnitude to a color ramp, the magnitude to a color, I should say, and set the pixel to that color. Voila. If you're lucky and rainfall has been somehow magically measured at locations on the surface of the Earth that coincide with the pixels that you're drawing, then it's particularly easy. All you have to do is set that correlate that rainfall value, that measure, to an intensity, and you're done. Well, sometimes actually, by the way, it's not even a measure that you're a measurement or a sample. It's simply a calculation. This is a very easy sort of heat map to make. You are not measuring anything. You are simply doing calculations at every pixel. This is a distortion diagram, by the way, for an uncommon sort of map projection. More often, though, you're hoping that it's the heat map that's going to generate those pixels for you. It's going to provide the density measure as opposed to you providing the density measure. This is because your data set probably doesn't describe a phenomenon that occurs regularly in space. or won't be sampled as a regular grid in space, or even if it has, it probably won't have been at the resolution you might want for your visualization. So notice we have these bazillions of points here. Some of them, a very few of them are individual points and you can discern them, but most of the time they're just piled up on top of each other and you have no idea how many are even present in one place. This is where the intricacies of heat map understanding and implementation come into play, and mostly what this talk is about. This map is easy to make, easy to interpret, and doesn't need fancy algorithms to decide what color ought to be plotted at each pixel. This map, on the other hand, is hard to make well. It can be hard to interpret and requires a lot of calculation using concepts from statistics and signal processing in order to arrive at each pixel. So let's focus on how to make this map. Our data set consists of incidents. There is no measure, something happened, and that's the data point. We have a lot of those. That we have a lot of those it's important. There is no measure, something happened. A heat map is fundamentally a statistical narrative. If you don't have a lot going on, you don't have statistics. You have anecdotes. Here's a map of neighborhood crime incidents. What does this map tell you? Well, it tells you a burglary happened on 8th Avenue between 31st and 34th Streets a few years ago. Let's make a heat map. Or should it look like this? Or maybe this? The answer, of course, is none of them. This is not a candidate for a heat map. There is no statistic. Therefore, there is no density. There's no density, there's no heat map. What about this? These are Starbucks locations. We have a fair amount of data, but notice that most of it is spread pretty thinly. Just showing the raw points would be better over most of the map. In the heat map version, all we have done is smear them out uselessly. But as the points become dense, they become more suited to presentation as a heat map. Let's look at maybe a more apt example. This data set consists of 234,000 points, and as you can see, they're pretty dense everywhere where there are any at all. Here, a heat map makes good sense. You can clearly identify real hotspots of activity, but you can also still see the underlying striations in the structure of the data, reflecting the rectilinear grid that the taxi hailing events are constrained to. The phenomenon hasn't been blurred out of its structure, and its representation doesn't fabricate statistics where there aren't any. Obviously, if we were to zoom way into a couple of blocks, we're back to anecdotes instead of statistics, and we no longer have a good candidate for a heat map. What is it about a heat map's construction that depends on this notion of a statistic? How do we arrive at the intensity or hue of color to render? These concepts are tied together. A heat map purports to show density, so we need to compute a density for the phenomenon, but density depends on a measure per unit space. What area unit do we choose? The answer is, it depends. It depends on the scale of the phenomenon in relation to the scale of the map. If your map's scale and scope is such that you have hundreds of samples for every pixel of your map, then you'll probably be just fine counting within the pixel bounds. Choose an intensity proportionate to your count and draw the pixel just as if you had some continuous measure at that location. This might be what you do for a world heat map of human population, for example, since most pixels would contain a lot of people. But what if your data set is a lot more sparse? Here's where heat maps become aggregators of data. You have to choose what is called a kernel size, which simplistically is the number of pixels away from the center of the pixel you want to draw, within which you are willing to aggregate incidents. If you specify a kernel size of 8 pixels, then you would aggregate all the incidents within 8 pixels of the center and use that as an intensity value. Your map then becomes a visualization of incidents per 200 square pixels because 200 is about the area of a circle of radius 8. If 200 square pixels represents a square mile, then your map would, in essence, show incidents per square mile. As this kernel slides over the map, incidents fall off of one side and enter into the other, and so every pixel ends up with its unique calculation for incidents per square mile. Notice that I keep using the word aggregate instead of count. There's a crucial reason for that. Not every incident carries the same weight to the pixel we're creating. This only makes sense. The further away the incident, the less it should contribute to the heat that the pixel conveys. I don't know if the subtleties of intensity are going to come through here, but you can see that the pixels that are further away from the center are lighter. That's because we are weighting them less. In fact, even though we chose an 8-pixel radius in our example, what we're really saying is that the contribution of anything beyond that is practically 0, not actually 0. That's how we keep the computation to something manageable. So what we end up doing is multiplying each incident, which is a count of 1, by some fraction, the size of which is smaller the further away it is from the kernel's center. You can imagine there might be different ways of choosing the weight based on distance. How we map distance to weight is called the decay function. There's no particular right way to do that, but good ways to do it all look pretty much the same and pretty much mimic what's called a Gaussian weight function. Once we've summed all of these weighted incidents, the result is the pixel's heat that we're looking for in a heat map. The tricks here are in choosing a meaningful kernel size, a meaningful decay function, and a meaningful color to represent the aggregation that the kernel performs. The software you use is probably going to be pretty good at choosing a weight function, the decay function in essence, but it's probably not going to have any idea what to use for a kernel size or what your color scheme should be. So, what about that color? Back to our Starbucks map and some variations. Which of those 3 is right? Well, that's the beauty of heat maps. None is, or any is. You can just take your pick. That's also the kind of the weak point or the flaw in heat maps. Here we have what looks like a very hot concentration of Starbucks shops. Is it justified by the data? We've done a couple of things to translate the data into this particular heat map. We chose a large kernel. Why did we do that? We also chose to amp up the intensity sort of exponentially instead of something that looks more linear. Why did we do that? The effect is that we have obscured the nuances of the information right there in the hotspot. It's just one massive blur. So in this circumstance, I would suggest that maybe these choices aren't justified. That doesn't mean they never are. If you have some phenomenon that's normally quite constant and the consequences of it deviating from the norm are great, then maybe you should be amping up the intensity. Take, for example, golf course soil samples. You have a resort that wants to keep their golf course green, very green and uniformly so. So every week they take nitrogen samples and very close measurements of what's going on with the fertilization. And the thing here is that a small deviation of the fertilizer is going to have a very large effect on the turf. A little bit too little, and the turf is going to be sparse and stunted, and a little bit too much, it's going to be all burnt. So rather than showing the intensity linearly with the amount of nitrogen that they've applied, maybe they should be showing the effect if they applied too much of it. And so you might have some kind of curve like this for your heat map and the intensity that you choose. So likewise with our taxi pickup map. We saw the weekend map, but what about the weekday? By using a different intensity ramp than we use for weekend, we can make the two look a lot like each other. And on their own, that's probably fine because the pattern of pickups is truly very similar. But juxtaposed against each other, we probably would rather that the weekday intensities be scaled down so that they are proportionate to the weekend versus weekday incident count. So consider whether your map is going to be juxtaposed against other of similar data, whether that's ones that you generate or ones that are just out in the wild already. And by the way, if you can't even control how the measure translates into color intensity, then maybe you should consider finding some other software. So far, we've only looked at heat maps that use one hue using different intensities to convey magnitude. But we've all seen heat maps that use a continuum between two colors or even a rainbow scheme. So yeah, what about that rainbow scheme? Here's a crime map. Regions with fewest incidents are blue, intermediate are green, and the highest are red. I'm going to say right up front, I have no idea if this has been adjusted for population or not. I don't know if this is incidents per capita or if it's just raw incidents. So already we have a problem of interpretation, but getting beyond that and going back to the color, what is the map trying to say about crime? Normally we think of green as being optimal or all clear, and yet the people subjected to intermediate levels of crime probably wouldn't agree that they're at some optimal level of crime. You know, something more toward blue is what they would hope for, or maybe even no color at all. Is no color at all a good thing here? I don't actually know, because I don't know if no color at all coincides with no incidence of crime or lack of data. See the blue fringes? What does that mean? Are those regions of low crime? No, not really. That's where the kernel has ended, basically. And so, is that a problem of interpretation, a problem for interpretation? Well, you betcha. So, why does the map even need green? Why doesn't it just use a single hue for intensity, since that's really what we're talking about, a phenomenon that is one axis? How about this geothermal map? It's a nationwide map of geothermal potential. At first glance, this might seem reasonable. The coolest regions are blue, the warmest regions are hot. But again, we're stuck with this green in the middle. Why? Are those the most desirable regions for exploiting geothermal energy? No. Is green somewhere between blue and red? No, not really. Does green reflect some norm? No. In other words, it's arbitrary. If it's arbitrary, it's probably not good for interpretation. There is one set of conditions I can think of that is pretty good for rainbow usage. Let's look at this map of temperature departures from normalcy. Here, green is what you might expect. Good, normal, healthy, natural. Blue to purple signals below normal to way below. Yellow to red signals above normal to way above. Now, I mean, I don't like the Windows 1990s graphical quality, but other than that, I think this is probably pretty fine. So you might want to think about that anytime you're tempted by the classical rainbow. And you should also, by the way, think about the semantics of the color scheme you choose for single-axis phenomenon if you're tempted to choose more than one hue. There is the problem here on this one of people with limited color vision. So, I mean, I think it's fine for me, but I don't have that problem, and a fair number of people do. So you should probably take that into consideration. And last of all, you'll probably expect me to go on some rant about map projections, because that's pretty much what I do. So here you go. Two different locations on the globe, but same area measure on the ground, same phenomenon density on the ground, totally different apparent density on the map. Are you convinced? Can you do something about it? Well, maybe. If you just have some local area phenomenon, then don't worry too much about it. If you're mapping on a Mercator, you just need to adjust your area calculations for the latitude. You can refer to a paper that Battersby and I wrote on hex binning for how to do that. If you're mapping a more global phenomenon, just forget about Mercator. It's not going to give you anything useful. I know that most people's software is operating on that, but it's just too bad. What you're putting out doesn't work. Instead, you need an equal area projection. This is a sinusoidal, but that's going to be wrong too if your kernel operates on the map instead of on the sphere. And this is wrong. How do we know it's wrong? Well, down at the equator, we have circles, basically circles for the intense portion of phenomenon. You look up at the high latitudes, they're still circles. What do you know about the sinusoidal? The sinusoidal is distorting these things into ellipses, but those aren't ellipses we're looking at. It's wrong. This calculation is happening on the map instead of on the globe. It's wrong. So in summary, if you don't know the details of how the heat map got constructed, whether you're looking at one or whether you made one by plugging parameters into a software, then maybe just forget it. Don't use the heat map. If you don't dig deeper, then you'd be lying to yourself, and you may even be lying to your audience. Now, so hopefully I've scared you out of using heat maps for a lot of purposes. Here's a summary of how to think about some heat maps so that you don't get caught up by some of these problems. And meanwhile, we can take some questions. So it depends on the density per area. If you have 10 burglaries that are spread out widely on a map, then no, you still don't have a heat map. If it's 10 burglaries in a very small area, and your map is just that very small area, you have like a tiny graphic or something, sure, why not? It's purely about density. Sorry? You want me to come up with a formula for incidents per area? Yeah, I can do that, but I'd have to put it up later.
All right, thanks, Dan.
Yeah, thanks.